Ask My Instructor 10.1.59. Use the remainder term to find the minimum order of the Taylor polynomial for e to the x centered at 0 that is required to approximate e to the 0.03 to 5 places. Assume capital M equals 2 and find n such that the remainder term will be less than, or the absolute value of the remainder term will be less than this number. A short review. I can just hear you groaning now. I'll try to make it quick. Suppose f has continuous derivatives up to the n plus 1 derivative on an open interval I containing a. Let x be a point in that interval. The nth order Taylor polynomial for f with center at a is given by this summation. The difference between f and its nth Taylor polynomial is called the remainder. It is the error acquired when the nth polynomial centered at a is used to approximate the function at a point x. The question then becomes, what kind of error do we introduce in using the polynomial to approximate the function? Now, Taylor's theorem is actually a pretty powerful theorem. It says that for a given value of x, there is a value of c between x and that center a such that the remainder equals this value. Now, this is what we call an existence theorem. It only says that this c exists. It doesn't tell us how to find it or where it is. All right, now we're comparing this remainder term with c with the polynomial. It kind of looks like the first neglected term. If you remember the alternating series theorem, it kind of looks like the first neglected term, and that's how I remember it. However, it is different from the first neglected term because the evaluation is at that magical value c that's between x and a. And again, all we know about c is that it exists. So you might feel like, wow, big deal. However, it is helpful because if you can, for that derivative, if you can find a bound on that n plus 1 derivative, then you've got a bound on the remainder. And so that's what's going on. So that big M that they gave you, big M equals 2, they're telling you that the derivative, the n plus 1 derivative evaluated at c is less than or equal to 2. All right? All right, so they say that we can assume that this n plus 1 derivative evaluated at this magical value c is less than 2. Now, I can hear you groaning again. I want to show you where something like that comes from. Why can you make such an assumption? This is within your ability. And again, I'll make it fast. If I run through the derivatives are all just e to the x. And so the absolute value of the nth derivative, or the n plus 1 derivative, I should say, is e to the c. So the absolute value of the n plus 1 derivative is e to the c. And so remember that the c is going to be between 0 and 0.3. So c is between 0 and 0.03. Again, I've got that typo. It's bugging me. It's that n should be n plus 1. So if you could please just make a mental note there. All right, now e to the 0 equals 1. So if I go e to the c, that's going to be between 1 and e to the 0.03. Now, you know that e is less than 3, and you know that 0.03 is less than 1. So a really comfortable bound would be 3. And I can easily do a bound of 3. Now, where they got a bound of 2, I'm not really sure. They probably cheated, but our bound of 3 would work just as well. It's not a big deal whether it's 2 or 3. I'm going to use 2 because they said to use 2, but but um, but we could have used 3. All right, so since that nth derivative is going to be 2, then I have a bound on my remainder term. And we want to know how high n has to be for my remainder term to be small enough. Let's see. X minus a. Well, a is equal to 0, x is equal to 0.03, and so this is what I get. Now, I want that to be less than how many zeros is that? 0.00005. And I'm going to write it in scientific notation. Whoa, what happened to the absolute value sign? Well, I don't need the absolute value sign because 0.03 to the n plus 1, that's certainly positive, and n plus 1 factorial, that's so positive, it's obnoxious, it's so positive. All right, now we want to find n such that this value is less than 5 times 10 to the negative 6. Now, factorials. You probably have not experienced dealing with factorials in an algebraic manner. And so I think the best thing to do is to switch to technology. And since I'm on a computer, I'm going to use Excel. Now, if you don't know how to use Excel, you can program your calculator or just do a trial and error. You'll see it doesn't take long. But I like Excel. It's kind of fun for me to use. So if you do know Excel, I'll show you how to set it up. So I'm setting up the columns not for n, but n plus 1. So set up the columns for n plus 1. And then in the cell B2, this is what I type. So the factorial you can find that function factorial, it's F-A-C-T. And then I just click on, for the A2, I just click on A2. I don't type in A2. And the reason why I click on it is that when I do a copy and a paste, it works. All right, then if I click on the check mark, I get 0.06. Then I do a copy and paste. And the interesting thing with Excel is that when you paste down, you don't get the A2, you get A3, A4, A5, you get the appropriate cell, which is cool. All right, so when you do that, you get this. All right, now we have to be able to interpret this. All right, now for n plus 1 being 3, I have 9 times 10 to the negative 6, which is too big of an error. And so I'm not going to use n plus 1 equals 3. That's too big of an error. Now, n plus 1 equals 4. If I interpret their notation, I write in scientific notation, this is what I get. Now, that's clearly less than 5 times 10 to the negative 6. So that is well under my needed error. So that n plus 1 being 4, that works great. So if n plus 1 equals 4, so n plus 1 has to be bigger than or equal to 4, which means n is bigger than or equal to 5. And we're all done here. Take care.